Okay, in this video I'm going to be sort of introducing the idea of waters of crystallization. And I won't be going into in this video how to actually work out the waters of crystallization. I just want to sort of explore the general idea of what it actually is and what are these stuff. I'll go into that as well. Okay, so to understand the idea of waters of crystallization, I want to take a look at an example structure of this. And before I draw that up, this here is a powdered form of copper sulfate, CuSO4, copper sulfate, and this is also copper sulfate, CuSO4. Except this version is slightly different to this version, as you can see. Now, what's different? Now, this version of copper sulfate has water incorporated into the structure of it. But the water incorporated into the structure isn't actually bonded to the ions in the structure. It's not bonded to the ions. Now, because it's not bonded, and we want to represent this as a formula, and it's quite close to the actual the ions in the compound, but it's not bonded to them. Because of this, we want to include it in the formula, but we want to make it explicitly clear that the water is not bonded to the ions. And in order to do this, as you can see, I just drew a dot here, and what we do is we draw this sort of subscript dot to represent the fact that what we are going to write after this dot is not covalently bonded to what we've written before the dot. And in the case of waters of crystallization, what is not bonded to this but is sort of close to it is the water molecules. And so we would have a number after this to represent the number of water molecules. Obviously, if it was 1, we wouldn't have a number, but if it was any number apart from 1, we would have a number. So I'll just put X here, so any number. And then we'd have the H2O. And what this would mean is that for a given number of moles of this ion, of this compound, CuSO4, copper sulfate, we would have X number of moles of H2O, and it's a definite ratio between them. So this is a definite ratio. So if we have any number of CuSO4, let's say we had 2 multiplied by CuSO4. So if our compound contained 4 moles of CuSO4, whatever the definite number is of H2O, which usually bonds to 1 mole of CuSO4, would be bonded. So we would have 4x H2O, and this is just like algebra. So yeah, we would have, if we had 4 of that, we would have 4 extra moles of the H2O, whatever number of H2O that usually is. I think it's usually 5. It's usually 5, and sometimes it can vary, but it's usually 5 for copper sulfate specifically. But for a specific compound, it's usually a specific number of moles of H2O which bonds to it, and that usually doesn't change as the number of moles of the compound increases. Okay. So if we were to take a look at a sort of what's happening on a molecular level, I guess we would describe it as a molecular level, probably. If we were to take a look at what's happening on a molecular level, and we imagine that the copper, because we have the copper ions and the sulfate ions, I'll draw the copper ions as green dots and the sulfate ions as red dots, just for effect. Actually, blue dots. Blue and red seems to work quite well. So the blue will be positive and the red will be negative. So these blue dots are copper ions. Copper. Oop. There we go. Copper. quite big actually. Yeah, so these are the copper ions, and between these copper ions are the sulfate ions. So here are the sulfate ions. And as you can see, they form a sort of regular pattern. And this would continue down here somewhere. And with the blue. And basically between this layer of ionically bonded ions, they're ionically bonded, we would have water molecules. So we'd have, well, let me decrease the size of my pen. Let me do the water molecules in light blue. So we'd probably have water molecules like here, maybe here, etc. We'd have just like lots of water molecules in here, and these water molecules would be attracted to the different ions in a specific way, because water molecules are polar molecules, and since they're polar, which means that the oxygen atoms in the molecule have a slight charge, because we've got like the electrons are quite slightly closer to it than to the hydrogens. It's got a slight charge, and that slight charge is slightly negative, and the hydrogens have a slight charge, and that charge is slightly positive, because they're sort of being starved of these electrons. See, so the electrons are sort of up here closer to the oxygen, and oxygen's also got extra atoms up here, because it's extra electrons up here because it's got two lone pairs, so electrons that are not bonded. So this molecule would be here. So you can imagine that if this slightly positive part would be more attracted to the slightly negative, which I said was the red ones, slightly negative, than the slightly positive blue ones. And so the oxygen, which is slightly negative, would probably be more attracted to the slightly, well, not the slightly, but the positive ions. So the copper ions, the positive copper ions. And this is sort of how they occupy this space, and this is an integral part of the structure of this crystal, which you can see. Now the forces which are acting here are probably Van der Waals forces, something like that, but they're not covalently bonded to each other, the water molecules and these ions, but they do form an important part of the structure. And since these water molecules are inside a crystalline structure, as you can see here, between these layers of ionic lattices, since they're in the middle of this crystal, we call these water molecules, we call them water. I think we would call them waters of crystallization. And this is a weird sort of form of plural. Correct me if I'm wrong. I think it's waters. It might be water, but I think it's waters of crystallization. And so a crystal, the form of this copper sulfate with the waters of crystallization, we have a special name for it. And the word water, it can also be represented by the word, can also be described by the word hydro. And in, I think it's Greek, hydro means water. So hydro would mean water, and then we have a US at the end, so it's water, it's with water, so it's hydrous. It's a sort of nature of it. The nature of this crystal is that it contains water, and so this is what we describe this substance as. And this one doesn't have water, because this had to be added, we had to add water to this to make it like that. This doesn't have water, so we can sort of use this same sort of language style and say that it doesn't have water, and the way we do this is we say that it's anhydrous. Anhydrous. And as you can see, this anhydrous means without water. It doesn't have that water nature to it, and as you can see, the physical, the visual properties of the molecule look slightly different. And so yeah, this can change into this by the addition of water, and this can change into this by heating in order to get the water to leave it. And in the next video, I'll walk you through basically working out the number of moles of water molecules in a given hydrous crystal. So yeah, and I want to make it clear that for a given number of moles of this compound, so in this case it's CuSO4, we have also a specific number of moles of the H2O. So yeah, I just wanted to make that clear. So yeah.